Survival regression involves utilizing not only the duration and the censorship variables, but using the additional data as well. This additional data is known as covariates and usually include gender, age, salary, and other characteristics that define the population under study. We regress these covariates against the duration variable. The datasets used for survival regression needs to be in the form of a data frame with the column denoting the duration of the subjects, an optional column indicating whether or not the event of interest was observed, as well as additional covariates you need to regress against. Like with other regression techniques, you need to pre-process your data before feeding it to the model for training. The algorithm that we will focus on is the Cox proportional hazard regression model. This model takes into account the effects of several variables at a time. It also examines the relationship of the survival distribution to these variables. It is similar to multiple regression analysis, but the difference is that the dependent variable is the hazard function at a given time t. It is based on very small intervals of time called time clicks, which contains at most one event of interest. It is a semi-parametric approach for the estimation of weights in a proportional hazard model. The parameter estimates are obtained by maximizing the partial likelihood of the weights. Gradient descent is used to fit the Cox model to the data. Gradient descent finds the way such that the error is minimized. The formula for the Cox proportional hazards regression model is given as follows. The model works such that the log hazard of an individual subject is a linear function of their static covariates and a population-level baseline hazard function that changes over time. These covariates can be estimated by their partial likelihood. Beta 0 is the baseline hazard function, and it is defined as the probability of experiencing the event of interest when all the other covariates equal 0. And it is the only time-dependent component in the model. The model makes no assumption about the baseline hazard function. It does assume a parametric form for the effect of the covariates on the hazard function. The partial hazard is a time-invariant scalar factor that only increases or decreases the baseline hazard. It is similar to the intercept in an ordinary regression. The covariates or the regression coefficients x give the proportional change that can be expected in the hazard. The sign of the regression coefficients, beta I, plays a role in the hazard of a subject. A change in these regression coefficients or covariates will either increase or decrease the baseline hazard. A positive sign for beta I means that the risk of an event is higher, and thus the prognosis for the event of interest for that particular subject is higher. Similarly, a negative sign means that the risk of the event is lower. Also, note that the magnitude, which is the value itself, plays a role as well. For example, for the value of a variable equaling to 1 would mean that it will have no effect on the hazard. For a value less than 1 will reduce the hazard, and for a value greater than 1 will increase the hazard. These regression coefficients beta are estimated by maximizing the partial likelihood. Cox proportional hazards model is a semi-parametric model in the sense that the baseline hazard function does not have to be specified. It can vary, allowing a different parameter to be used for each unique survival time. But it assumes that the rate ratio remains proportional throughout the follow-up period. This results in increased flexibility of the model. A fully parametric proportional hazard model also assumes that the baseline hazard function can be parametricized according to a particular model for the distribution of the survival times. Cox model can handle right censored data but cannot handle left censored data or interval censored data directly. There are some covariates that may not obey the proportional hazard assumption. They are allowed to still be a part of the model, but without estimating its effect. This is called stratification. The datasets is split into n smaller datasets based on unique values of the stratifying covariates. Each smaller dataset has its unique baseline hazard, which makes up the non-parametric part of the model, and they all have common regression parameters, which makes up the parametric part of the model. There is no regression parameter for covariates stratified on. The term proportional hazards refers to the assumption of a constant relationship between the dependent variable and the regression coefficients. Thus, this implies that the hazard functions for any two subjects at any point in time are proportional. The proportional hazards model assumes that there is a multiplicative effect of the covariates on the hazard function. Cox's model makes three assumptions as explained here. The hazard ratio of two subjects remains the same at all times. The explanatory variables act multiplicatively on the hazard function. Failure times of individual subjects are independent of each other. You can go to my article on Towards Data Science to learn more about other survival analysis models, including Allen's additive model and the accelerated failure time model. Now let's create a Kaggle kernel using survival regression analysis to prevent customer churn.